Good morning, my name is Nadav Albel and I will present my master's thesis work. It's called Partial Correspondence of 3D Shapes Using Properties of the Nearest Neighbor Field. It is a seminal work under the supervision of Professor Ryan and Professor Lee Tselman. So let us begin. We'll go over a short introduction. We'll then see the previous works in the field. We'll then get to a general approach. We'll present the core of our method, which is the similarity function. And finally, we'll show some results. So after the introduction, we'll go over the problem statement, the motivation, why do we even want to solve this problem, the challenges inherent in solving this problem, and our key ideas we implement in order to solve it, and finally, our contributions. So, what is shape correspondence? Well, we have some base model denoted by M here, and some partial deformed version of it called N, and we want some correspondence between. Correspondence is hard to define rigorously, but basically we want to match the point of the ear to the point of the ear, the tip of the paw to the tip of the paw. We want them to be exact, and these are sparse correspondence. We want to get to dense correspondence. So if we color the model, every vertex in the model here, by its XYZ coordinate, the correspondence on the part will be denoted by having the same color. This is our results, by the way. It doesn't have to be this perfect, but it does. So this is the correspondence. If the color is the same, then it's a corresponding point. Okay. Why do we even want to solve it? Well, I don't know if you know this person. This is Andy Serkis. He is an actor. He has played the role of Gollum, Emperor Snoke, and in Planet of the Apes as well. And I haven't met him. I'm not a mind reader, but I would guess he would not want to wear this suit all the time. So animation transfer is one use for it. Other uses include non-rigid registration, repeating pattern recognition, time-varying surface reconstruction, and more they are they specify them in the survey which is cited here. Okay, what are the challenges? Well, first, bodies, especially living beings, undergo non-rigid transformation. It means you cannot just solve for a rotation and translation of the model. And let's look what happens. Local shapes get deformed. If you would just look at these two patches, these two geometries, you wouldn't know they are the same thing. What else? Well, partiality. Because of how we acquire the data, a lot of parts get occluded. For example, if the camera would be in the back of the room, my hand would occlude my chest, and the tables would occlude the rest of my body, so a lot of the data will be partial. What happens when the data is partial? Well, let's look on the distance, the shorter distance from the tip of the paw to the nose. This is on the full model, and let's look to the partial model. It gets extended, it gets deformed because it needs to bypass all the holes there. And more than that, let's look at local shapes here. They are unrecognizable. And last but not least, topological noise. Because of the resolution of the sensors, when bodies which are distinct lie near to each other, they fuse. So this is without topological noise. This is the shortest pass from the foot to the tip of the hand. Here you have the thigh and the calf fusing. It gets shorter, and there the hand is on the thigh, the legs are fused, and it gets even shorter. This is notoriously hard to solve. Okay, so what are our key ideas to handle this? Well, first we use similarity, which is based on statistical properties of the nearest neighbor field. What are these statistical properties? And what is the nearest neighbor field? Let's go over what is the nearest neighbor field. So let's assume we have the shape M and N illustrated here, and they have a local shape descriptors in them. So the nearest neighbor field is just the arrows, the nearest neighbor assignment of each local shape to its nearest neighbor in the part. We want this to be diverse. Diversity is distinctors of matches. So if you look at the right illustration, the arrows converge to a single point. The matches converge, they are not diverse. And if we look at the left model, the arrows all point to different points, which is good for us. It is high diversity. And we also want the distance of the matches to be consistent. So again, we have two illustrations. In one, on the right, the distances extend, not good. Our match should preserve them. So to sum our contributions, we present a new approach for 3D shape correspondence. It is robust to partiality, topological noise, and non-rigid deformations. And we exhibit state-of-the-art results on various benchmarks. For example, this is the former state-of-the-art Rodola 16 on steroids with much harder parameters. You can see here that the hand is mapped incorrectly. It's good in our result, and the dog as well. The legs are flipped, not happening in our case. So this is some motivation for you to keep in focus for our work. Okay, so we'll briefly go over the previous work in the field. We'll start with full surface matching, then partial matching works which handle topological noise, and finally we'll see some relevant work from the 2D domain. Why? Because our inspiration is taken from works in the 2D domain. Okay, so what about full surface matching? This problem is a fundamental problem in 3D and graphics and computer vision. So a lot of work has been done on it. The one class of works handles local descriptor distance minimization. Another line of works, they try to minimize pairwise relations like the geodesic distance we have seen on the dog. We try to find the matching which minimize them. Other works try to embed shapes into canonical space where they can solve for rotation and translation. And finally, like almost everything in the field these days, machine learning architecture has been employed. The best one is from 2017 of Ori Litani from computer science in the Technion. I think he is Kimmel's or Bronstein's student. Let's see what he had done. Well, he concocted a network where he put inside local shape descriptors, and he learns the descriptors which produce the best results for functional matching, which is an embedding into a canonical space of the matches. So if you have the points here denoted in blue, red, green, the net predicts the probability of the points to be in a certain location, and it maximizes the probability to be in the correct corresponding location. What about partial matching? Well, a lot works there, a little less than full matching. It is a harder problem. The rigid domain, they solve for rotation and translation, a lot of works there. In the non-rigid domain, the first works minimizes pairwise relations, but regularize it by some partiality priors. Partial functional correspondence, one of the state-of-the-art line of works. It is embedded into a canonical space, again modified with a prior for partiality, and like anything in the field, machine learning has been the most recent line of works. The best reported results, full reported results on the benchmark are of Bostine in 2016, even though it is not the latest work. So what they have done there, instead of using a grid, they have used geodesic patches and employed an anisotropic kernel, which corresponds to the curvature of the surface. You can see the filters they have learned by this network, and they managed to get nice correspondences. Okay, and what about topological noise? Even less work has been done with that, because this, like I said earlier, is notoriously hard. So some works try to derive some robust properties which will be robust to these shortcuts. Functional matching as well tries to handle this. Got a pretty good result, was state of the art until 2017. some machine learning has been tried to tackle this, and the best work was a combined optimization. We'll go over it. So what they have done here, they used local shape descriptors in combination with heat kernels, pairwise heat kernels, which describe how heat propagates on a surface. And they did a joint optimization on them, and they got a match which is continuous and is locally coherent and got the best results until now. What about 2D template matching? Like I've said, this is the inspiration to our work, the works here. So the problem is pretty analogous. We have a template denoted in the green rectangle here, and we have an image that we want to search this template in. It has undergone some deformation, might be occluded, so you can see how the problem is pretty much analogous. You can try to minimize all the pixels distance, like in works you've seen on surfaces, but this was not as successful as other works which I'll get to. So the inspiration to our work handles statistic of low-level feature, in this case image patches. So best bodies similarity, they counted as reliable matches, only those, the green arrows here, where the patch in the template considers one patch as a nearest neighbor, and the same patch in the search window consider it a nearest neighbor as well. So a mutual relationship means a reliable match, and they just counted this. Okay, another work done under the supervision of the esteemed professor sitting in the front row here is deformable diversity similarity. So here, instead of counting mutual relationships, they counted the diversity of the arrows. Let's look at Q1. All the arrows converge to very few points, so the diversity is low. And in Q2, all the arrows are distinct, so this is a high diversity. In addition, they have used a geometrical consistency measure, here denoted by the length of the arrows. So if you overlay P on Q2, the matches would produce these short arrows. And conversely, on Q1, you see all the arrows are long, which means the geometrical consistency is really low. Okay, if you have been out of focus until now will be a good time to refocus because we get to our body of work. So let's start with our general approach. Our key ideas, well, the similarity, which is the core key idea we've already introduced in the introduction, should be diverse, and pairwise distances should be preserved. In addition, matching should be done on smaller subsurfaces. Why? Well, let's look at the dog again, and let's look at these local shapes. So the distances don't preserve over all the surface, but if you look locally, they preserve pretty well. In addition, we use multiple subsurface sizes. Why? Look at the front paw here, and look at the hind leg, and look at the hind leg on the other model. The front paw here looks more similar to the hind leg if you don't have the context of the dog's head. So we need the dog's head, but it won't preserve the distances, so we start from coarse, we have the global context, and we go to a final level to localize it. Okay, a short overview of our pipe. We have the base model and the part we want to match to it. We start with the nearest neighbor field calculation, extract patches, use those two, the nearest neighbor field and the patch extractions to calculate the similarity measure, find some initial match, and finally we refine the matches according to their coherency. And now let's dive into the details of each stage. So nearest neighbor field calculation. As our input, we have the two models, M and N, and the goal is to produce a nearest neighbor field, a mapping of every vertex on M, the full shape, to its nearest neighbor in some local shape descriptor space on M. The key idea is to use a local shape descriptor with the following properties: robustness to small deformation and partiality, and sensitivity to symmetrical flips, because we don't want the right leg to be mapped to the left leg. Okay, so we start with estimating normals for every vertex on the surface. And then we look at a local environment of some vertex. And we calculate something called FPFH, fast point feature histogram. So we collect all the points in the neighborhood of some point. We calculate local reference frame for every point, and these reference frame have some angles between their axes. We put these into a histogram, and this is our local shape descriptor, and then we derive some matches from the full part to from the full model to the part. You can see it's very noisy. It's not a good correspondence, but it's good enough for our framework. You will see how we refine it with our similarity. Okay. Now we have our nearest neighbor field, and we extract patches. This can be done in parallel because it is not dependent on the formal stage. So the input, again, is the two meshes. And the goal is to obtain a representative set of vertices of the part N. We do this to save complexity. The similarity measure is pretty computationally expensive. So we want to produce a sample which covers the surface. And in addition, we extract a set of subsurfaces for the sake of similarity calculation. So the key idea is to sample N and begin with salient points, points which will be easy to match, and extract overlapping subsurfaces at multiple scales. We have seen why in the key ideas. Okay, so how do we sample the parts? Well, we want to start with the extremities, the tips of the leg, the tip of the tail. How do we do that? Well, we start with calculating geodesic distance for every point to all the others, and we calculate the sum of distances for every point from the other, and local maximas of this sum are the extremities. You can see the tip of the tail as a local maxima, and you have two maxima on the legs. So we start our sample set with that. So now the regions near these samples are covered, but we need to cover the entire surface. So because they are covered, we can define a forbidden region. We don't need any more points from the red region here. And we add more samples on the boundary of the region. And we continue this iteratively until the entire surface is defined as forbidden. Now we have a nice coverage. This looks like the suit that Andy Serkis wore. And once we have these samples, we extract patches around each sample at 3 scales, which are some fraction of the area of the full model. So you can see here, around this point, we extracted 60% of the square root of M, 40%, 20%. This is of the part. What about the base model? We don't want to lose resolution here. We want to localize it well, all the points. So we extract densely the patches around here. Okay, now we have the nearest neighbor field and the patch extraction. We can continue with calculating the similarity. I will go briefly over the key ideas here, and we'll delve more deeply into it after I finish the pipe, because this is the main part of our work. So the input, we have our nearest neighbor field, and we have the set of surface patches. We call them QJ for the full part and PI for the partial surface. And we want to compute a similarity score, which maximizes when the correspondence is correct. So if the point, we try to match the point in magenta here, we want the similarity denoted from black low to white high to be maximal in the correct point on the front of the form. The key idea is to calculate the similarity, which rewards high diversity and penalizes pairwise distances. Like I said, we'll go over it in detail later. For now, let's assume we have calculated it and see how we continue from there. So, initial match. We have our similarity for all the pairs of patches at 3 scales, and we want to extract a set sparse correspondences for all the samples in the part. Key ideas, the calculated similarity, we want the most similar points to be correspondence. So we take the maximals, and we use a multi-scale approach. We have 3 similarity scores for each pair of patches, and we use this, we'll see how shortly. So Our part for this example is N, the front of the cat here, and the point we try to match is marked in magenta. And we calculate the similarity. This is 60% of the radius of the full model. And you can see that the similarity maximizes on the front of the paw, but it's not well localized. It's on the upper side of the leg instead of on the paw. What happens if you would only use a single scale and take a 30% size patch? Here you don't have the head of the cat, so we don't have global context. And it maximizes, as you can see, on the hind paw. Look at M there, this is the maximum. So it's locally better, but globally incoherent. And we can go even further down, and same thing, even better localized, but on the wrong leg. So instead of using the scales separately, we use a multi-scale approach. We start from the highest scale, we obtain the match there, and we use it to constrain the maxima we consider as good to a neighborhood near it. So now you can see the match is more localized, and we continue it to the finest scale, and this is our final correspondence. Okay, we have an initial match, but look at the tail here. You can see some of the matches are still incorrect. So we want to refine our match. So we have as our input a set of sparse correspondence. We'll call them VI and WI hat for all the samples. And we want to detect incorrect matches. Our key idea is most matches, as you can see, are already correct. Only some points on the tail are incorrect. So incorrect matches should be inconsistent with respect to most matches which are correct. And we want to detect outliers. So let's look at one grossly incorrect match, WJ, VJ. And let's look at the neighborhood of the 2 points and the geodesic distance of each vertex from them. As an inconsistency measure, we took just the difference of geodesic distance from all the matches in one surface to the other. So we have this point and we have some other match. And here you have it and the source of it. So we have the geodesic distance encoded in yellow here, deep blue here, and the arrows are encoded by the difference of geodesic distance. So you can see most arrows here are yellow, teal, some of them are blue, but overall this is inconsistent with other matches. What happens with correct matches? We do the same, and here you can see the reverse. Most of the arrows are blue, and some of them, the incorrect matches, are encoded in yellow. So the inconsistency for a match will be just the sum of all these geodesic differences. And how do we detect outliers? We just threshold it by the mean inconsistency of all the matches times some coefficient which has been found empirically. So if it is higher than this threshold, we mark this as an outlier. So here, the red correspondence is marked as an outlier in our algorithm, and the green one is still good. Okay, we have detected these outliers. Now, we still want all the surface to be covered, so we want to replace them with better matches. So we have a set of good correspondence and a set of bad correspondence denoted in the red circles here. And we want to replace bad correspondence with correct one to get fully coherent correspondence. So we already calculated the incoherency. We would like to minimize it. And we have our similarity. We want the local shapes to still be similar, so we use that as well. So we have our bad match. We have our similarity, and you can see that it has a maxima where we have found the initial correspondence, but it has other maximas as well, and one of them is in the place it should be, on the tail. So we search for a local maxima of the similarity, which has the lowest inconsistency score of all the other maximas. So we do a small search, and hopefully in the end we get the correct match which is the case for this model. So this is the end of our pipeline. We got a good set of sparse correspondence, but we would like to get dense correspondence. So we can just input this correspondence to another algorithm which produces dense correspondence as a delta function, and as you can see, it densifies pretty well. Okay, we've skipped over our similarity. Now we'll get more into it in detail. So how do we calculate the similarity between two subsurfaces? We'll start with the key ideas. We'll define diversity. Then we'll show what we define as the geometrical consistency. And finally, we'll get to our combined similarity equation. So just to a reminder where we are in the pipe, just before we extract the matches, similarity is for extracting them. And the input we have is the nearest neighbor field and a set of patterns. Here I've only put two on the screen because we show how we calculate the similarity for two surfaces. So, and we want to calculate the similarity score which maximizes for correct correspondence. So what are the challenges? Let's remember. Non-rigid deformations, local shapes don't look the same. Partiality, local shapes look even less the same, and geodesic distances are inconsistent, and finally, topological noise affects local shapes and geodesic distances even more. So the key idea of the similarity, let's reiterate, usage of statistical properties instead of trying to minimize low distances. We want to reward diversity and to penalize geometrical inconsistency. So what is diversity? Here we have a small example, and the arrows denote a nearest neighbor relation from local shapes on Q, which is from the full model, to local shapes on P. And the diversity is the number of points of local shapes on P, which has a local shape Qj in Q, which considers it a nearest neighbor. So here, P1 has an arrow pointing to it. It will add 1 to the diversity. P2 has 4 arrows pointing to it, but we are only interested that it is pointed to at all. So this is +1 to the diversity, and P3 has nothing pointing to it, 0 diversity, contribution to the diversity. What about geometrical inconsistency? How do we measure it? Well, we don't have a grid like in images, but these were constructed around some reference points, these two portraits. So we just use these centers as a reference. We measure the geodesic distances, and the geometrical inconsistency, like in the refinement step, is the difference of geodesic distances from the reference point. So here the geodesic distance is high, here it is low. We calculate the difference, and this is the inconsistency match, which is high in this case. Okay, some examples before we will show how we combine these two. So when surfaces are the same, you can see a lot of lines pointing to distinct points, and the inconsistency is low, encoded by a blue, deep blue color of the arrows. When we have the same shape but deformed, still a lot of distinct arrows, most of them deep blue. Some of them are inconsistent, but they are the minority. What happens when we have only shape, but the reference point is shifted? We still have a high diversity because all the shapes are there, but you can see a lot of teal lines here, which account for inconsistency in the geometrical unit. And when the shapes are not related to each other, then a lot of yellow lines, most of them converge to very few points. Okay, so how do we combine these two ideas? So we have an inconsistency score for every arrow, and we find the most consistent arrow denoted by Ri star. If a point in P doesn't have an arrow pointing to it, then we denote its inconsistency as infinity. and we sum over the 1 divided by Ri star plus 1. Well, it's easy to see how this relates to geometrical inconsistency. What about diversity? Well, let's make the following thought experiment. Let's assume that arrows, the Ri stars, get either 0 or infinity. So we have the best arrows which are 0, we have arrows which are more than 0. We don't take any stock in this, and obviously we will have infinity. What happens to this, the value of what we sum? It becomes either 1 or 0. Effectively, it just indicates that a point P has an arrow pointing to it. And in this case, what happens to the similarity? It can be denoted by the following formula, which you have seen a few slides before. It is the definition of diversity. So this formula encapsulates well both diversity and geometrical inconsistency. In the general case, we don't just count the arrows. We give them the score of their geometrical inconsistency. So R2 is inconsistent, it will get 1 divided by 11. P2 is more consistent, 0 difference, it gets plus 1, and P3 has nothing pointing to it, plus 0, and we do it for all the matches on both surfaces. This is our final similarity calculation. Okay, now to the nicest part of the work, the results. So we'll introduce the data sets we've evaluated our method on. We'll then show some qualitative evaluation, quantitative evaluation. We'll show how robust our method is to a different choice of our parameters. We'll go over the complexity of calculating the correspondences, and finally some limitations, some areas that still need improvement in further research. Okay. So we have 3 benchmarks. The first of them is called Shrek 16, partial matching of the four ball shapes. It is divided into 2 subsets. The first one is cuts. So you have a base model in a neutral pose, and you have a different version of it, and it has been cut by a plane, so you have one nice cut, one nice piece. The other subset of this benchmark, a bit harder, is holes. They picked the surface around it. So you have a very regular boundaries here. Another benchmark is called Shrek 16 topological noise. You have 10 models of the same kid, but with different types of topological noise. Different limbs intersect. This is a very hard benchmark. You have 10 models, and you try to match each pair to one another. 90 problems in total. And finally, we want to show that our method works for real-world data, so we've evaluated it on Faust, which contains real-world scans of humans, and you have some topological noise in some cases. You have partiality. So let's see how well do we do in this. So let's begin with our results on partial matching. Let's concentrate on the cats there in the upper corner. And I think that my friend here has told me that even humans wouldn't be able to say that this is a cat if they just saw the model. But as you can see, we matched it pretty well. The legs are all matched correctly, the face, the head of it is matched correctly. And you can see on the other models as well that the color transfers pretty smoothly, which indicates a good correspondence. What about topological noise? We have some nice results here as well. The most impressive for my taste is this, because look at the hand here, it is fused to the foot on one model and to the side on another, and still it managed to find the correct match. And finally, real-world scans, very good results here as well. Okay, so this is only our results. How well do we compare to other methods? We've compared ourselves to Odola 16, partial functional correspondence. They provided us with the code and the default parameters. actually better parameters than what they have used in the evaluation. And you can see that you have a lot of symmetrical flips. Here in the horse, the front leg is mapped to the hind leg. They are good, they are fantastic, they are brilliant, but they have some problems. What about us? Let's start with sparse correspondences. And the points here are colored by what our algorithm thinks they are corresponding to. And you see it's pretty well. And now let's densify it. And you can see that the colors almost transfer smoothly from one surface to the other. And we can show the errors of each method. Denoted from white, no error, to black. You can see Rodola 16 has some errors. Most of them are symmetrical flips. And our models are almost all colored in white. This is for partial matching. What about topological noise? Well, you have some places where Rodola failed completely. It is more local than global. And ours is better. Still, especially in the case of symmetrical flips. You can see the arm here is flipped in Rodola, and it is correctly matching our algorithm. And finally, real-world scans. This is Rodola's results, and these are ours. And again, the most salient feature are the symmetrical flips in Rodola, which are not present in our methods. So these are anecdotes, these are small visual examples. What about quantitative? First, we'll show what is the error method, what is the quantitative method. So suppose we have a vertex V and a ground truth correspondence W star on the base model. And our algorithm manages to estimate W hat. So the error will be just the distance of the estimated correspondence to the ground truth correspondence, normalized by the area of the full model, analogous to a radius of a sphere. So first we'll show cumulative curves. We'll explain what you see here in the graph. So the x-axis is the error thresholds. So what is below here is our matches that are below 5% error threshold. And the y-axis is the percentage of correspondences that fall below this threshold. Like it is written here, higher is better. You have dense correspondences denoted by a full line, and you have sparse correspondences denoted by dotted lines. And ours is in magenta here. We report both because our pipeline outputs sparse correspondence and we then densify them. And you can see that we are better than the latest state of the art by around 10% on the 5% error threshold. The black one is what we have used to densify our matches, and you can see we are 10% better than it as well. This is on the cut subset of the Shrek 16. What happens on the holes? Well, here we just beat the benchmark by more than 20%. So pretty impressive results, if you may ask me. I hope so, at least. Okay, it is traditional to report another error metric on here, which is a mean geodesic error. This was the x-axis in the last slide, as a function of partiality of the model. The higher we are, the further we are along the x-axis here, the more partial the model, the less sparse we are in the model. And you can see here that our mean error is low, and it's more indifferent to the partiality than other methods. Okay. What about topological noise? Well, here we are only second best. The top spot is still reserved for Wessner 17, which we have seen in the related work. But Wessner 17 doesn't work well for partiality because of the high complexity in this case. And the parameters were tuned for the case of topological noise for Wessner 17. We use the same parameters both for partial matching and for the topological noise. So we have some advantage here as well. And But like I've said, we have some parameters we need to tune. They were all tuned on a test set provided with Shrek 16. We've only tuned it on the cuts subset. And the first one is beta, the sizes of the geodesic patches. And you can see here that different choices, different reasonable choices make almost no difference. The larger gap between any two curves here is around 3% of matches. And in the bottom row, you can see the parameter we've chose finally. We also have the outlier threshold coefficient. And here you can see almost no effect at all. Well, most of the correspondences are good enough even if you don't use this stage. This only helps for a few models like the cat where it takes the tail and completely corrects it. The maximal gap here is around 1.5% at the 0.1 threshold. And what about the radius of the local features, the FPF edge? Again, at most 3% between the curves here. So it's pretty robust to the choice of different parameters. It has a lot of them, but the choice of them, any reasonable choice, will get a good result. Okay. What about the complexity of the method? Well, nearest neighbor field calculation, we need to calculate the low-level features. FTFH, we calculate it for each point, which is the n here. And for each point, we need the complexity goes as the number of vertices in the neighborhood, the radius of the FTFH, which is denoted by k. And then we compute approximate nearest neighbors, which takes n log n on average. Patch extraction, here it is dominated by the calculation of geodesic distances. Calculating geodesic distance on the surface for one point is n log n, and we do it for all the points. So it's n squared log n. Similarity, well, calculating for 2 points, like for this pair, we'll take an order of O of n. We start with a 60% radius, which is almost all vertices in the shapes. So this is why this is O of n. And we do it for S samples. Remember, we have sampled the part. And to all n vertices on the base models. So this is O of S n squared. Initial match, just finding the maximum of each similarity. O of n times the number of samples we find it for. Outlier detection, we already calculated the geodesic distances. It's just summing them for each match with respect to other matches, and we do it for all matches. So O squared. And the outlier replacement, we already have the maximas of the similarity. We already have the distances. So again, going over them for all samples and for each sample. Effectively, we have the abstraction, the geodesics, plus the similarity, O of S times n squared. For a problem of Shrek 16, it took us around 60 seconds on average to solve a problem. And it's pretty good with respect to other methods. So finally, some limitations. What do we still have to solve? Well, we still fail at extreme deformations. Here you have the cat crouching, the legs are all curled up, the tail is near the legs, and local shapes are unreliable. Our method relies on local shapes as well, so we might fail in this case. Heavy topological noise, our method relies on geodesic distances, and sometimes you have leakage of correspondences from one point to the other because of this. And finally, we don't tackle parts to whole here. We try to match the full part to the partial, to a partial version of it instead of the other way around, and we don't know how to filter what we don't need to match. So it's still an area for research. So the problem, we tackle it well, but you can't say the problem is completely solved. This is an interesting research to take. I had a lot of fun working on it. Some motivation. Next step. So I want to thank Professor Ali Tselnik and Professor Ayel et al. I would be willing a year ago to satisfy with mediocre work, not what you see here. And they pushed me to produce something which helps me go outside with my head held up high. So thank you for that. Thanks to Professor Ben-Hamo sitting here, Dr. Ben-Hamo, sorry, not Professor, my lovely wife, which supported me through all the hardships. And thank you to Dr. Uri Volner, which is not here, which helped me edit the paper, and I don't think I would be standing here if not for him. So this has been it. Thank you very much. Any questions?